There's another one over there. Hello? Yeah, what?
Sound waves.
And our observatory open weekend. Just a reminder that to the east of the Visitor Centre is a community market where you have various things for people to enjoy out there. If you're looking to go over to the telescope, you exit the back doors of the Visitor Centre and follow the crowds over to the blue tent where you will be marshalled for your tour. Please be patient, there's probably a line-up if anything to go by from yesterday. And for those around 11 o'clock, we have the first of our lectures for the day.
Yeah, I don't know.
Dr. Will Hall, the Deputy Director of the Australia Telescope National Facility.
To be as non-technical as I can make it, but if I'm if I don't get that right, then please stop me, ask me questions, or even if you have things that I just haven't explained that you're interested in, I'm really happy to have interruptions as we go through. Okay, so ask me questions. There'll be plenty of opportunity for questions at the end too. I won't be running away, but if you'd like to interrupt as we go, that's fine. I'm really comfortable. Radio astronomy countries in the world, without a shadow of a doubt. It's up in certainly the top 3 or 5 countries. The USA is very, very strong. The Netherlands, very strong. Germany is probably the other one that I would put in there, and maybe the UK. Astronomy is, in some sense, the highest impact Australian science. One of the ways of measuring impact of science is to look at how many times the research results of scientists working in a field are referred to by other researchers. That's a measure of impact. It's not much point conducting science that doesn't influence any other researchers, that has no carry-on, if you like, for what we're talking about. So strength of the background emission as a function of frequency in Sydney, with a population of 4 million, there's an awful lot of radio noise around. At Narrabri, where we have our other observatory, and Parkes is comparable to this, you can see that there's much less. There's much less of the spectrum that has lots of noise in it, and it's also weaker, although the peaks are around about the same strength, 120 up here, roughly 120 here. In Murchison, with our population of 4, you can see that there's an awful lot less background noise. We still have satellites going overhead, satellites which are transmitting radio power all the time and so on. There is still noise there. We can still detect, I think these are radio transmissions coming from Geraldton. We have a problem here with digital TV transmitters, which switched on a year or so ago, well 2 years ago now, on Mount Sugarloaf near Newcastle. Right. These are incredibly sensitive machines.
It's going to orbit Saturn. It's been there for about 3 years now. And flying by the moons and the rings in and analysing it and studying it in great detail. And then piggybacking on board was the European probe called Huygens, or the European Space Agency. And it was designed almost about a month or so after it arrived at Saturn. It was going to detach and actually descend down through the atmosphere of Titan. And as it descended, we'd taken photographs and sending data back. And so that if you had one transmitting there, one, you'd be guaranteed that the mother craft would see one at least at some point to guarantee some redundancy. And so they realised that what they would do, pointing 30 degrees from the Earth, which meant if you could link lots of telescopes on the Earth together in a very long baseline interferometry network, you can actually pinpoint the position of the Huygens probe in the atmosphere of Titan to within 1 kilometre. And by measuring the Doppler shift from the mothercraft against what you're seeing on the sky, on the Earth, you can get a profile of the winds on Titan as the thing was descending. So you can do a little wind experiment, see how the atmosphere of Titan.
Express to Mars, passing within 50 kilometres of your position.
We have you on screen, Elysium 7. Your passengers might be interested in seeing some images we have been compiling from our telescopes. Would you like me to transmit them?
I was rather hoping that you would.
We have been doing a survey of the locations of galaxies beyond our own Milky Way. Our Sun is just one star among billions in the Milky Way, and each of the galaxies here contain nearly as many stars. The light from these galaxies has taken hundreds of millions of years to reach our telescopes.
How long would it take us to fly to the nearest star to our solar system?
At the speed your ship is going, a little over 1 million years.
I think we might just stick to Mars on this trip. Thanks, Midway. We will check in on our return journey. This is day 89. As we prepare for our aerobraking orbit, we are getting some great close-up views of the 2 Martian moons. The first of these is the smaller moon, Deimos. And here is some file footage of Phobos. They look quite similar to each other, don't they? They are only tens of kilometres across and are probably captured asteroids. Although Mars has very little water, it does have incredible polar ice caps. The northern cap is mostly frozen carbon dioxide on a water ice base. The reddish streaks are layers of dust deposited during huge dust storms. We are making our approach at a height of 85 kilometres above the surface. Towering ahead of us is the largest of the surface features, the volcano known as Olympus Mons. It is 27 kilometres high. That is 3 times higher than Mount Everest. The volcanic crater at the summit is about 70 kilometres wide.
And that becomes some of the technology, what they call synthesis technology, where 1 kilometre in diameter, in terms of the resolving capability or the pinpointing capability. And that's what synthesis technology happens up at Narrabri.
How do they do that exactly with that?
Well, that's because with ours we've already like a fixed surface area, so if it's bigger or smaller, it's basically fixed by the feeding the base of all their resolution. It'll just pick up the specific signature of what the pulsar is.
Within a whole bunch of information.
Yes, that's right.
then they can say, well, that must be
Magnetic pole of what was the star is in our line of sight, so we get to see the burst of energy. So there's probably a lot more pulsars out there that we don't see because they're spinning maybe around that way, it's like pulsar in orbit around each other. And they've just recently discovered that there's actually 2 pulsars in orbit around each other. Sensitive radio, basically. It's basically has the capability of taking the signals which bounce off the surface of the dish. They would travel up into what we call like a feed horn structure like that. Right. That one's not for this particular receiver, but there's a similar sort of feed horn which would be attached to the bottom of the receiver under here. Yeah. There's a piece of waveguide. So basically the signals come off the dish, there's free space propagating waves, but they get funneled through a waveguide into a horn, or through the horn into the waveguide to become like, a transmission system. They go inside into this dewar, which is a high intensity vacuum, and inside that we have what we call low noise amplifiers. This is just an example of what the internals of a receiver might look like. So inside here we have like a cold plate, and there are amplifiers which are mounted on that cold plate. And what we do is, with this particular motor or fridge motor and a cryodine, and using helium gas as a refrigerant, we actually cool the internals of this plate in here, the actual amplifiers, down to about minus 250 degrees Celsius. So it's about 20 Kelvin above absolute zero. Right. And the reason why we do that is that all electronic devices produce thermal noise, like the background hiss that you might hear on your radio. Part of that is the signals from outside, but a lot of it is actually the internal electronics of your radio making like a background hiss. And what we do is, because we're trying to pick up very weak signals from space, we have to minimise that hiss or noise from the actual front-end electronics. So we cool these things down, and by cooling them down, you minimise their actual thermal noise contribution. Like another post-amplifier processing plate, there's further amplifiers there, and filtering, conversion, and those signals then get sent down. It was initially designed and built to act as a receiver for supporting the ESA Giotto mission back in '86. Giotto flew through the tail of Halley's Comet, and that was at X-band at a different frequency. And once that mission was complete, we then modified this receiver so it then became what we call a methanol receiver, where it operates at 6 gigahertz and up to 12 gigahertz.
So you will stick a new receiver up in a telescope depending on what line you're looking at.
Exactly. For us, like you imagine again with your AM, FM radio, you twiddle the knob as you close up the door. It's all buttoned up and it becomes nice and quiet. You have to have specialised filters to get the signals in and out, electrical signals. So for your monitor, your keyboard and mouse, and things like that, they go through a specific filter. So obviously with a filter, having an electrical connection, you do degrade the effects of the Faraday cage a bit. As long as you've got sufficient filtering, it's actually quite enough. What we're trying to do with some of the technology that we're building is to actually see whether such a gravitational is actually generating a gravity wave. So you're doing research at gravity waves here? Yeah. Let's see the pictures of Einstein.
There was? Walk up to it. Yeah. It would have happened. here in the sun for a minute, thaw out. Just gather round if you can. That's the division of CSIRO that operates this observatory, and we also have a large observatory up outside Narrabri, the Australia Telescope Compact Array. I don't know if anybody's been up there and seen that. There are 6 antennas up there, 6 22-metre antennas. This is a 64-metre antenna. So up at Narrabri we have 6 22-metre antennas that are linked together as what's called an interferometer. We use those as an array. We have another 22-metre antenna just near Coonabarabran, which we call Mopra, just named after the rock that it's sitting on. And the grand old lady, the Parkes telescope, as I said, 64 metres across. What we're going to do is go up through the tower here, come out around the azimuth track where you can see the other tour up above us, go up another couple of sets of steps, up another 2 stories up into what's called the alidade, that's the rotating part of the structure, and then we'll come back down through the centre and have a look at the control rooms and the computer room and so on as we come out. When we go in, we'll go pretty much straight to the upstairs control room. I'd ask you just have a look as you come through, but if you could come through fairly quickly, we'll see everything as we come back down. So it's not like I'm trying to rush you past all the interesting bits. We're just going to go through, then slow down, have a look around as we go up the outside section, and then spend some time as we come back down through the centre. It's vermiculite. You might remember vermiculite from the ceilings of apartments and things like that, and houses. This is a heat shield. So you notice that there's a gap underneath. There's an air gap all the way up. Come around here. Around that track and up another couple of sets of steps up the outside of the structure. Is there anybody who's particularly uncomfortable with the heights? Just come around from about here, mate. Back up the road a bit. That the telescope's sitting on. So simply on the flat track, there are 4 cylindrical rollers. 2 of those are driven, 2 are just idlers. As I said, only gravity holding the telescope down. There's a pintle bearing in the centre that keeps the telescope centred, but it's simply sitting on this track. What we're going to do is go around this way. As we go, we're going to go past one of the azimuth gearboxes. This large box that's hanging out the outside here that's driving the telescope. So there are 4 15 horsepower DC electric motors. And if you just have a quick look, if you're interested as you come past, you'll be able to see that the motor is actually turning. You can see the commutator inside through that perspex window. The telescope at the moment is tracking. So what we're doing is observing a fixed point in the sky. But a fixed point in the sky doesn't stay stationary with respect to the Earth, because the Earth's rotating. And what the telescope is doing at the moment is constantly moving to correct for that rotation of the Earth. It's moving incredibly slowly, and it's usually very hard to tell that it's moving, but if you line up something like the edge of one of these wipers against some reference point, and if I talk for long enough and then you look back, you might be able to tell that the telescope's moved a little bit. But certainly the motors are turning, it's driving the telescope all the time. So if you just come round with me here, the telescope itself, that was actually the first parabolic antenna used for Columbia, Australia. It's called Kennedy out in the US. Inside the counterweight, with a structure on both sides of us and across the back is the counterweight balancing the dish. So essentially 450 tonnes of steel, concrete and lead. The rack gears that you can see now up either side, the 2 Zenith gearboxes and 2 more of these 15 horsepower motors, identical motors just here and here, driving through the pinions onto those racks. Those of you that are over far enough, if you look up this side of the counterweight on the inside, you can see a hole there. That's half of the doorway. When we get up further into the structure, I can show you the other half that lines up. Inside that doorway, there's a ladder that goes up through inside the counterweight. It'd be a bit of a challenge to get up the ladder at the moment because you'd be hanging upside down underneath it. But when you tip the telescope up so it's pointing vertically, those doors line up, the ladder's vertical, and we can go through there and up inside the counterweight and up to the higher levels of the telescope. Around, we'll have plenty of time to get out of the way. It's actually good fun if it does happen. So we'll just see how it goes. Maybe come a little bit past me, might make it easier.
Must have taken an enormous crane to lift the counterweights in position when they built the thing.
Yeah, I think a lot of it was actually concrete slurry mixed with lead that was put in place.
Oh, once it was up.
And, yep, and also there's a whole series of boxes you might have seen welded on. The new focus cabin's bigger and heavier, which means you need more counterweight.
Yeah.
And each of those boxes is filled with a ton of lead shot. We can do astronomy 24 hours a day, 7 days a week in principle, because the sky isn't bright at radio wavelengths, so we can do radio astronomy all day, every day. We schedule about 80% of the hours in the year here for astronomy. 20% of the time we use for maintenance and upgrades. So, I mean, we need to do constant maintenance. This is now a 46-year-old machine, incredibly well engineered. Most of the major engineering that you see from the outside is original, but we need to constantly look after it, and we also constantly upgrade the systems. Everything from the receivers all the way down through the signal path is totally upgraded on quite a short time. There's an interesting pattern here in the track. You notice that? That. The telescope's perfectly positioned to see this. Anybody tell me what it might have been?
Stone?
Pardon?
Stone?
No, it's a spring washer.
Yeah.
Oh my god!
It got stuck on the roller, which is why you can see it every 40 centimetres or so. Each time the roller came around, it pressed it into the track again.
What happened eventually when I pressed it in?
I don't know.
It just became...
So we're going to go up onto the rotating part of the telescope. We won't be going into the tipping part, but once you come up on here, if you have a look in this first door, you can see what we call the twister room or the wrap room. One of the challenges of operating a telescope or designing a telescope is that you have all sorts of cables that are attached to things that are fixed into the tower, which doesn't move, and they need to be connected to things which are up in the rotating and tipping part of the structure. Pointing out in the counterweight that there was a hole in the side of the counterweight in the doorway. This is the other half of the doorway. So looking through here, this is the inner wall of the counterweight, and that door that we were looking at in the counterweight is out there somewhere behind us. So when the telescope if we tip the telescope back up, counterweight comes back down, and these two doorways line up, and you can go through there and into the counterweight and up higher. So telescopes are pretty dangerous places because of these sorts of actions in doorways. An astronomer actually was killed in the US, very experienced astronomer, about probably 15 years ago now, when he went through a doorway at the wrong time and the telescope was moving.
Oh, really?
So it is important that we actually know what we're doing around the place. This centre column here is completely separate from all of the outer parts of the building and the structure itself. There's no mechanical connection between this and anything that we're standing on. So if the telescope was to start to drive quickly, what would happen is that the floor would rotate around this. You'll swear that the centre column is moving, but it's not, it's us, if that was to happen. The reason this is completely separate, has its own foundations into the ground, is because sitting on top of this is part of the guidance or steering system, if you like, of the telescope, what we call the master equatorial. When we're trying to track a point on the sky, we're not actually directly driving, not directly controlling, if you like, the direction in which the radio telescope is pointing. What we do is directly instruct the small telescope that's sitting on top of this to point and to move in the right way, and we slave the radio telescope to it. So there's a laser sitting on the radio telescope, pointing straight down the axis. When the two are pointing together, we pick up 4 equal voltages being reflected off a mirror in front of the optical telescope, and we simply constantly ask the question, is the radio telescope pointing the same way? If it's not, then we move it. So we don't instruct it directly, we simply have a master-slave system. That works very well because you've got 1,000 tons sitting on this structure, which vibrates, it moves, it distorts, but none of that gets transferred to the thing that is actually determining where we're pointing, which is the master equatorial. So a brilliant design implemented by Barnes-Wallis. Some of you might know about the bouncing bombs, dam busters. So Barnes-Wallis was the British engineer that designed that. He also designed some of the critical elements of this telescope.
Way might be a bit of a problem too.
Too big for me.
I'm a small little so I have to follow my friend.
We have to stop.
I think that's all right. It'll be a problem
I mean, it's sort of creepy because everything's groaning and creeping, you know. We're not working for radio, so we don't like. Okay, I was just asked about the fact that Bob Menzies found the money to build. This telescope was actually partly funded by Australia and partly funded by the US, so money came from the Rockefeller Foundation. It was built primarily by a German company, MAN. They constructed and assembled most of the moving parts in their factory in Germany, then disassembled it, shipped everything out to Australia, started to put things back together again. The dish itself, the large parts of the structure, were all welded on site, and my understanding is that all the welding was done at night to ensure that the material was at a uniform temperature before it was welded together. The surface that you see, 64 metres across, 54 metres of that is now covered in perforated aluminium, and that's the highest accuracy section of the surface. That surface is within about 1 millimetre of the shape that we want it to be across that 54 metres. So it's a phenomenal structure. Coming back to the funding though, we have actually just secured $120 million to build a new telescope, the next generation telescope, which we will be siting in Western Australia. We have a site in Murchisonshire, and Australia is one of the leading contenders to host what's called the Square Kilometre Array, which is a telescope something like 1,000 times more powerful than this. Current cost estimate is €1 billion. There are 17 countries currently collaborating to do that. At the moment, well no, this is for a Pathfinder telescope. It's not for the Square Kilometre Array itself, but we're building what's called the Australian SKA Pathfinder, and that is, if you like, about a 1% of the Square Kilometre Array that we'd like to build. We will, Australia would only ever put in about 10% of the Square Kilometre Array here. This is what we use to drive the telescope up and down if we're doing maintenance. If we need to get people on the edge, we drive the telescope right down to the ground. You can step up onto the edge of the surface, drive the telescope back up, stow it, put the pin in, turn it off and go away. You can do that from the manual control panel here. The signals that we're trying to detect come out essentially. So the signals from the receivers and the focus pattern are brought down to this level. Depending on the type of astronomy that we're doing, we can either configure this a good way for me. Control system, and we may have to configure things by hand using the patch panel here. So this is these racks contain a whole heap of amplifiers, attenuators, filters and so on, and our staff will come and configure this for the astronomers ready for use, together with the data as references for later processing. There's an atomic clock out in a little shed out the back here, currently accurate to about 2 billionths of a second per day. And we use those as time standards. You can see on the display here 3 different representations of the time. The bottom large row is the Australian Eastern Standard Time. The top large row is Universal Time Coordinated, basically Greenwich Mean Time. So it's just about midnight. We're about to start the new day in UT. That's 10 AM local time. And the middle display is local mean sidereal time. Sidereal time tells you where things are in the sky. Because of the fact that the Earth is moving around the Sun, the sidereal time tells you where things are in the sky. Obviously important for astronomers to know. So if you can follow me around here a bit. Star trails where you see all these circles in the sky, where you do time-lapse photography of the sky. That's what you're seeing there is the rotation of the sky.
But in the north, they're lucky they've got the North Pole. Here you've got to go 100
They've got the
around
North Pole Star.
Yeah,
that's
the
right.
North Pole Star.
Yeah.
You just, oh, there it is, and you just set your little clock. Here you've got 100 around to try and find.
Yep. But it used to be that essentially all the computers in the telescope were in this room. We're progressively actually moving stuff out of here because as we get more and more sensitive equipment, the interference that our own equipment produces becomes more and more of a problem. I forgot to point them out when we were upstairs, but you might have noticed behind you as you came out of the, as we first came out of the spiral staircase, there's a whole stack of these large beige cabinets, steel cabinets, reaching most of the way to the ceiling. Those are radio frequency shielded cabinets, so they're Faraday cages designed to keep inside all of the radio emission that's coming from the computing equipment that's inside those cabinets. So we're shielding our own equipment so that we make sure that our receivers aren't detecting noise that's produced by the equipment that we're using to record and process the data that we're trying to collect. Just in front of you, just inside the window here, there are 3 generations of very specialised types of computers. These very large electronics boards are designed and built by our own research engineering group in Marsfield. Those are called correlators. That's what we use to basically analyse and sample the data that we're collecting. 3 generations there from the late 1980s, late 1990s, and on the right hand side the cab correlator boards are absolutely brand new. We're making those right now. We have the first working unit using those cab boards just installed upstairs as part of the Pulsar Digital Filter Bank. You can get an idea of the progression of computing here by looking at the basic statistics of these. Just as an indication of the fact that this sort of engineering is world leading. On Thursday this week I signed an agreement for CSIRO to provide 5 units based on this latest generation correlator board to overseas observatories.
Lovely to see you. Happy in our work, are we? Excellent.
Well, Willem, do you want to say briefly what sort of systems you're observing at the moment?
Yeah, sure.
You'll have to come over and speak up. We've got a reasonably big group, so really do crowd up this time and see if you can get around the door. So this is the main control room where astronomers tend to spend most of their time operating the telescope using a couple of the computers in there.
We're observing a type of star called a pulsar. It's the product at the end of a star's life. If you think of a normal star like our sun, you can fit approximately 1 million Earths inside of our sun. It's huge. But at the end of its life, it collapses under its own weight and gets crushed by gravity into something about 20 kilometers across. So it's incredibly dense. And if you think of a skater or dancer when they're spinning and they draw their arms closer to their body, they spin faster. The same happens to this star as it gets crushed under gravity, it starts to spin a lot more rapidly. The fastest spinning pulsar spins over 760 times per second on its axis. So you have something heavier than our sun spinning faster than the motor in your blender. It's quite unimaginable. This is a diagram of a pulsar here on the screen that you'll see as you walk by. It shows the compact core that I was talking about. And as well, you'll see some orange lines. They represent the magnetic field of the pulsar. Our Earth has a magnetic field with a north and a south pole. So does the pulsar. And out of the north and south pole is coming a beam of radio energy. And this beam is kind of like a lighthouse. Every time it swings around and faces Earth, we catch a blast of radio noise from space. And that's what we observe here with the dish.
Is the pulsar spinning at the incredible speed? Is it actually possible to say that it's stationary, or is it moving in space?
They do move in space, actually.
As long as I keep well away as well.
Yeah. In the supernova implosion, the matter doesn't fall in symmetrically, and you might have some falling in faster from this side, and the pulsar will get a kick. And pulsars actually have some of the highest velocities of objects that we measure.
Oh, so they're moving at great speed.
Yeah,
Oh.
yeah, like hundreds of kilometers per second with respect to the other stars. Yeah.
So what does the information
Scary.
look like that you receive? What does it look like?
Basically like a heartbeat.
So
Same way.
sound, is it sound? Or?
It's radio noise, broadband radio noise. So if you can tune it in on your radio, you'd hear something like clapping. In fact, we have an audio clip. I don't know if there's time.
Of course,
there's plenty of time.
Yes, there's plenty of time.
So this would be the sound of a pulsar. I'm not sure which one this is coming in over. Just if you put the radio signal through a speaker.
So which one is the information you get?
I don't know the details of this one. Sorry.
Which pulsar are you looking at right now then? You claim you're looking at?
We're observing a bunch of pulsars that were discovered recently using the Parkes Radio Telescope. So they did a survey through most of the 90s looking for new pulsars, and they found an enormous amount. Over half of the known pulsar population was discovered.
But in what area of the sky?
Okay.
Sorry,
we gotta go.
We're really going to...
Okay, Sagittarius, what?
Yeah, there's some in the Sagittarius. Yeah.
Willem's over in the marquee as well.
Sagittarius area.
Yeah. They're all over the place.
Just keep your helmets on as you can. Get over to the gate there.
Yeah, there isn't one. You have to do it.
Get out the gate.
May I say, that was fabulous. I went yesterday.
They can always come back.
Oh, yeah.
Besides in the visitor centre, over in the paddock adjacent to the telescope, there is actually some community locals over there. So go to your left and head up the
okay. Actually, I might get one too.
and a tour guide and take
Where
you
is
to
he?
the telescope.
He's around the front there.
It's in the shadow.
Yeah, that's what I tried.